I sometimes wonder where life actually begins, not in the poetic sense, but in the precise language of physics. If the smallest particles only follow the rules of energy and probability, then at what moment does a collection of atoms start to count as alive? The boundary is not sharp. It blurs into a gray dawn where chemistry and biology overlap so completely that the distinction becomes almost arbitrary. That question first occurred to me years ago while I was looking at images of gravitational lensing from the Hubble Space Telescope. In those distorted arcs of light, I could see entire galaxies acting as magnifying glasses, bending the path of more distant starlight. It was a reminder that most of what exists, even the matter we rely on to define reality, is invisible. And if the universe hides its structure so well, perhaps it also hides the nature of life itself. Tonight I want to take you on a slow journey across ideas that might seem unrelated. Here is one fact to anchor us as we begin. The first gravitational waves we detected on Earth started their journey more than 1 billion years ago, long before any complex organism moved across our planet. I often return to the idea that life does not begin with a spark or a miracle, but with a gradient. The earliest forms of organization on a young planet were not alive by any definition we use today, yet they were not entirely inert either. They were perched between two categories we draw for our own comfort, the non-living and the living. That border is neither sharp nor fixed. It behaves like a dawn, dim at first, then quietly brightening and never defined by a single moment. One of the most useful ways to approach the question is through energetics. A system can only persist if it draws energy from its surroundings in a way that favors its continued arrangement. A multicellular organism, for instance, does not simply appear because it is biologically elegant. It forms only when the step from single cell to multiple cells becomes energetically advantageous. If cooperation between cells reduces the cost of survival, then multicellularity can flourish. If the cost is too great, the system collapses back to simpler forms. This energetic logic applies all the way down. Even before life existed, simple molecules assembled and disassembled according to the energies of their bonds. Some combinations lasted longer than others. Some could trap energy from the environment. The moment a configuration of molecules found a way to stabilize itself, by channeling energy, it took a small step toward what we would eventually call life. At this stage, there is no consciousness, no metabolism, just chemistry exploiting favorable pathways. The grayness of this threshold becomes more apparent when we consider viruses. A virus cannot reproduce on its own. It carries instructions but no machinery. Outside a host, it is quiet, almost inert. Inside a host, it commandeers cellular processes and makes new copies of itself. Some biologists argue that this dependence disqualifies viruses from being alive. Others consider their ability to evolve and replicate as evidence of partial life. The disagreement itself reveals how fragile our categories are. Prions complicate the picture even further. They are simply proteins folded the wrong way. They contain no genetic material yet. They can persuade neighboring proteins to adopt their distorted shape. The result is a cascade of molecular mimicry. Prions do not eat, reproduce, or maintain boundaries, but they act with persistence. They spread. Their behavior echoes the logic of life, though they remain entirely within the realm of chemistry. These examples expose the inadequacy of simple definitions. Life is not a checklist. It is a spectrum of behaviors rooted in energy management. A molecule that can harness energy to maintain its structure acts slightly more alive than one that cannot. A cluster of molecules that can repair itself acts more alive still. A protocell that grows, divides, and competes for resources despite lacking genes is even closer to the first biological threshold. At no point is there a sudden leap. There is only accumulation. Carbon plays a central role in this ascent because of its extraordinary chemical flexibility. A single carbon atom can form 4 bonds, which allows it to create branching chains, rings, and complex three-dimensional structures. No other common element builds such elaborate scaffolds with comparable stability. Complexity is not optional for life. It is a requirement. Without intricate networks of reactions, energy cannot be captured, transformed, and reused. Carbon gives the universe a way to experiment with complexity, and Earth became one of its laboratories. Yet carbon is not the only possible foundation. Other worlds might offer different conditions with chemistry that favors alternative forms of structure. Perhaps, on some distant planet, sulfur-based molecules achieve a level of flexibility we have not imagined. Or maybe silicon, despite its limitations on Earth, becomes the dominant architect under different temperatures and pressures. If so, the gray zone between non-living and living there may look nothing like ours. It could be broader, narrower, or almost unrecognizable. The implications for life elsewhere in the universe are profound. Suppose we encounter a system that stores energy, replicates imperfectly, and evolves. Does that count as life? What if it lacks cells or membranes or DNA? What if it emerges from a chemistry entirely unfamiliar to us? Without a clear boundary on our own planet, we cannot expect the universe to follow our definitions. Many astrobiologists expect that if we eventually identify extraterrestrial life, our first reaction may be confusion. The system might resemble a peculiar form of geology. It might behave like a slow chemical network. It might fall somewhere between the categories we use to separate biology from environment. That ambiguity would not indicate failure. It would mirror our own origins. Earth teaches us that life emerges slowly through cycles of energy and structure. It builds step by step, each stage made possible by the one before it. The universe is not required to make the process dramatic. It only needs to offer the basic conditions, energy gradients, accessible chemistry pathways toward complexity. With enough time, matter explores those possibilities. Sometimes it discovers arrangements that sustain themselves. Sometimes those arrangements begin to compete, evolve, and adapt. And eventually, when complexity becomes deep enough, observers like us start asking where life began. The gray dawn between the non-living and the living is not a flaw in our understanding. It is a hint. It suggests that life is less a category and more a tendency, a direction matter moves when the conditions are right. This tendency does not guarantee biological emergence everywhere. It simply shows that the universe does not prohibit it. Far from being a rare exception, life may be one of the natural responses of chemistry exposed to time. As we explore more worlds, send more probes, and analyze more atmospheres, we may find traces of systems perched on the edge of animation, too organized to be called inert, too fragile to be called alive. Recognizing them will require humility. We will need to expand our ideas about what life looks like, what it requires, and how it begins. The gradual nature of life's dawn sets the foundation for the next question. If chemistry can blur boundaries, what about space and time themselves? Could the geometry of the universe admit structures as surprising as early life emerging, not from biology, but from curvature? This brings us toward wormholes, mathematical possibilities that stretch our understanding of what the universe might permit. Whenever we talk about life beyond Earth, we carry a quiet assumption that alien chemistry would resemble our own. Carbon, water, cell membranes, genetic material, these ingredients feel inevitable because they're familiar. Yet the universe rarely rewards familiarity. Its landscapes extend far beyond our intuitions, and its chemistries may follow rules that only partially overlap with ours. If life is a spectrum rather than a category, then the chemistry that supports it could be equally diverse. I often think about Titan, Saturn's largest moon, where lakes of liquid methane fill the valleys. The temperature there is unimaginably cold, far below the point where water turns to stone. Yet methane behaves like water in that environment. It evaporates, condenses, forms, clouds, returns as rain, and pools again into dark lakes. Chemically, this is a working cycle. A methane world follows its own logic. If complexity can emerge within that logic, then life might arise from entirely different foundations. Carbon remains a strong candidate for life anywhere in the universe. Its ability to form complex chains, rings, and networks gives it a structural advantage. Still, there is no rule demanding that all life must depend on carbon. Silicon sits just below carbon in the periodic table and can also create long chains, though silicon bonds tend to be less stable, especially in the presence of oxygen. On an extremely cold world or one with little free oxygen, silicon might play a more prominent role. The idea is speculative, but speculation becomes meaningful when constrained by chemistry. Sulfur offers another path. On Earth, sulfur-based microbial life survives around hydrothermal vents where sunlight cannot reach and temperatures swing between extremes. These organisms extract energy by oxidizing sulfur compounds, demonstrating that metabolism can take forms we once dismissed as improbable. Life adapts to available energy sources, not the other way around. If a planet favors sulfur chemistry, perhaps due to volcanic cycles or atmospheric composition, its living systems might follow that path. Extremophiles on our own planet give us countless examples of how adaptable biochemistry can be. There are microbes that thrive in acidic pools, organisms that survive beneath Antarctic ice, and bacteria that tolerate radiation levels lethal to most life. The resilience of these species often comes from their ability to harness unusual chemical gradients. In this way, extremophiles are reminders that metabolism is not a narrow definition. It's a process that captures energy, uses it, and sustains structure. The specific molecules involved matter less than the overall pattern. This leads to the core question: what counts as metabolism? If the chemistry is unrecognizable, a methane-based system might use temperature fluctuations instead of water-based reactions. A silicon-based organism might rely on slow, solid-state processes. Some hypothetical chemistries could support reactions measured in hours or days rather than milliseconds. If we encountered such life, we might misinterpret its pace as inactivity. An organism that completes one metabolic cycle per year might still be alive, just operating under a chemistry governed by different physical constraints. Alien life could also be harder to define because its interactions with the environment might not resemble ours. Imagine a system that stores information chemically but does not replicate in a familiar sense, or one that maintains complex structure but does not require a boundary like a cell membrane. A structure could grow, disperse, reorganize, and continue existing without ever forming a discrete individual. On a world governed by different pressures, the concept of individual organisms might not even apply. Scientific speculation becomes meaningful only when it respects what physics and chemistry allow. Temperature, energy flow, molecular stability, and environmental cycles determine what is possible. Titan's methane lakes remain stable because the cold keeps methane in liquid form. Venus's surface cannot sustain complex molecules because its heat and pressure destroy delicate bonds. Mars might have supported aqueous chemistry in the past, but today its atmosphere is too thin and too dry for water-based life at the surface. In this sense, speculation is not guesswork. It is an extrapolation from known constraints. Whenever scientists model alien metabolisms, they begin with energy. How does energy move through the environment? Is there a gradient that organisms could exploit? Could chemistry remain stable long enough for complexity to accumulate? Even speculative life must obey these basic principles. A system incapable of harvesting energy cannot maintain structure. A system with no means of dispersing waste energy cannot persist. Physics sets the boundaries of imagination. If alien life follows unfamiliar chemical pathways, our instruments may fail to recognize it. We tend to search for oxygen, methane, or carbon dioxide in exoplanet atmospheres because they signal biological processes on Earth. But an entirely different kind of metabolism might produce gases we overlook, or it might produce no gases at all. Biological activity could be locked in rocks, oceans, or subsurface layers. A living world might appear inert from thousands of light years away. Recognizing life requires understanding not only what life is, but what it could be. The gray boundary discussed earlier becomes more complex when extended beyond Earth. On another world, the threshold between the non-living and the living could shift dramatically. What we call prebiotic chemistry might persist for millions of years without crossing into recognizably biological behavior. Alternatively, complexity might emerge through routes Earth never explored, a different backbone element, a different solvent, a different temperature range. Each of these conditions leads to new chemical landscapes, new possibilities, and new challenges for identifying life. I sometimes imagine a distant world covered by a haze of slow-moving chemical networks where reactions propagate like ripples across a surface. No cells, no individuals, no DNA, just a planet-spanning metabolism evolving gradually as local conditions shift. To us, it might resemble geological activity. To itself, it might function as life. The universe has no obligation to align with our definitions. The most disciplined way to speculate is to accept that our sample size is still one. Earth may be typical or it may be peculiar. Until we discover a second example of life, whether microbial or complex, we cannot know whether carbon-water biology is universal or provincial. But while our sample is limited, our physics is not. Chemistry elsewhere must still obey the same quantum rules, the same thermodynamic pressures, the same constraints on bond formation and stability. Those constraints let us imagine without drifting into fantasy. Alien life might be stranger than expected. It could emerge from chemistries that defy our intuition but remain fully compatible with the laws of nature. It could be slow, diffuse, fragile, or unrecognizable. It could sit quietly on the edge of animation, waiting for a planetary cycle to tip it from organization into true autonomy. As we look outward and consider these possibilities, a new question follows naturally. If chemistry can surprise us, what about geometry? Could space-time itself support structures as unusual as a new metabolism. The first time I encountered the mathematics behind wormholes, I remember feeling something close to recognition, as if the equations were pointing to a structure the universe could have chosen even if it did not. Wormholes did not begin as fantasy. They emerged from Einstein's general relativity, specifically from the way mass and energy bend the geometry of space-time. If gravity is geometry, then the geometry can at least on paper fold, twist, and connect in unusual ways. A wormhole is one of those possibilities. The original idea dates back to the Einstein-Rosen bridge proposed in 1935. Einstein and Rosen were trying to understand how black holes might connect different regions of space-time. Their equations suggested a tunnel-like structure linking two sheets of space. It wasn't traversable, not in the way people imagine, but it was mathematically valid. The geometry wasn't forbidden. It simply folded in a way that created separate mouths connected through a throat. Topology is the key. Geometry concerns distances, shapes, and curvature. Topology concerns connectedness. You can stretch or twist a shape without changing its topology. A coffee mug and a donut share the same topology, each has one hole. Wormholes extend this idea to the universe itself. Two distant regions might be connected through a shortcut, a tunnel that ignores the ordinary limitations of space. It helps to picture space-time like fabric, not a flat cloth, but a surface that can be bent and sewn. If you imagine 2 points separated by a long distance on that surface, you could in principle fold the fabric so the 2 points touch, then stitch them together. That stitching represents the wormhole, a new route through space-time, not by moving across it, but by moving through its fold. The universe may even allow global connectedness without needing wormholes. If you traveled in what feels like a straight line for long enough, you might eventually return to your starting point. This idea is not prohibited by relativity. The universe could be finite yet unbounded, curved back on itself in a higher dimensional way. A straight path might loop around much as you can walk around Earth without encountering an edge. The presence of loops, folds, and higher dimensional connections hints that spacetime is far more versatile than our intuition suggests. Wormholes take this malleability further. They add handles to the fabric like tunnels carved through Swiss cheese. Some researchers imagine a universe full of such handles and tunnels at very small scales, a quantum foam bubbling with microscopic wormholes. At that level, the distinction between here and there may lose meaning. Space could be riddled with tiny bridges popping in and out of existence, influenced by quantum fluctuations. Yet a microscopic wormhole is not the same as one large enough for a spacecraft or even a single particle to travel through. Einstein's equations allow the geometry, but they do not guarantee stability. A wormhole tends to pinch off before anything can cross it. The throat collapses, the tunnel closes, the passage is lost. To keep a wormhole open requires something unusual: negative energy. Not negative mass in the science fiction sense, but energy with properties that do not occur in ordinary matter. Classical physics does not offer such material. Everything we observe in daily life obeys positive energy conditions. Structures built from normal matter cannot hold the throat open. This is where the mathematics becomes both tantalizing and humbling. Kip Thorne and others explored the problem by reversing the Einstein equations. Instead of asking what space-time geometry arises from given matter, they asked what matter would be needed to support a chosen geometry. If you specify the wormhole you want, the shape, the size, the path, the equations tell you what energy distribution would make it possible. And the answer consistently requires negative energy densities. Quantum physics, however, complicates the classical picture. The vacuum is not empty, it fluctuates. In certain configurations, those fluctuations can behave as though they carry negative energy. The Casimir effect is the most familiar example. When two metal plates sit extremely close together in a vacuum, quantum fields are restricted between them. The imbalance in fluctuations generates a measurable force that can behave like negative energy. It's subtle, but it's real. If quantum fields can create negative energy in tiny pockets, then perhaps the universe permits similar effects on slightly larger scales. The mathematics does not prohibit it, but we do not yet know how to amplify, harness, or sustain such energy. In the laboratory, the Casimir effect is delicate and small. It cannot shore up a wormhole throat. Still, its existence proves that negative energy is not an invention. It is a feature of quantum theory. All these details push wormholes into an unusual category. They are physically plausible within our best theories, yet far beyond our engineering capabilities. They rest in the space between permitted by mathematics and practical within the universe we inhabit. No natural wormhole has ever been observed. No experiment hints at a macroscopic one. They remain ideas drawn from equations, not phenomena discovered through telescopes. That doesn't make them trivial. The history of physics is full of concepts that began as mathematical curiosities, black holes, gravitational waves, even the expanding universe. Each one emerged first from equations, then from debate, then from observation. Wormholes might follow a similar path, or they might remain abstractions useful for thinking but never realized in nature. What matters is that the universe does not shut the door completely. The equations allow the geometry. Quantum theory allows the necessary energies, though, faintly and fleetingly. The puzzle lies in stitching those allowances into something stable, something that endures long enough to be meaningful. Whenever I consider wormholes, I think less about travel and more about possibility. They represent the freedom of space-time to shape itself in ways we have not yet seen. They remind us that the universe can be stranger than our ordinary experience suggests, yet still firmly within the laws of physics. That sense of possibility leads naturally to the next question. If geometry can permit tunnels and shortcuts, what kind of matter could hold them open? The idea of a wormhole is compelling, but its geometry alone does not guarantee its existence. Equations may permit the shape, yet something has to hold that shape in place. Without support, the throat collapses, the tunnel pinches shut, the entire structure becomes a fleeting mathematical mirage. To keep a wormhole open, space-time demands a particular kind of scaffolding, something unlike any matter we have ever handled, yet not entirely banished from the laws of physics. The starting point is simple. If you know the geometry you want, Einstein's equations will tell you the matter and energy distribution required to sustain it. Kip Thorne and his collaborators approached the problem exactly this way. Instead of speculating about unknown materials, they took the wormhole as a given and asked the equations to reveal what must reside inside it. This reversal, defining the curvature first, deriving the matter second, turns general relativity into a kind of architectural guide. You draw the shape, and the mathematics tells you the building materials. The result is as surprising as it is consistent. Any traversable wormhole demands matter with negative energy density. Not metaphorically negative, not simply exotic in the sense of being rare, but energy that carries the opposite sign from what ordinary matter provides. Classical physics does not contain such a substance. It does not emerge from stars, planets, gas clouds, or radiation. Every familiar form of matter obeys the positive energy conditions that help keep space-time well-behaved. Negative energy, however, is not fiction. It appears in quantum theory in ways that are subtle, fleeting, and difficult to amplify. The most accessible example is the Casimir effect. If you place two metal plates extremely close together in a vacuum, so close that only certain wavelengths of quantum fluctuations can fit between them, the imbalance in vacuum energy pushes the plates together. In some descriptions, the region between the plates behaves as if it contains negative energy relative to the surrounding space. The effect is small but measurable. Whenever I've shown students the mathematics behind the Casimir effect, there is a moment of disbelief. The vacuum isn't empty. Its fluctuations carry energy. Under the right constraints, those fluctuations can behave in ways that defy our classical intuitions. If such behavior can occur on a tabletop even faintly, then the idea of negative energy is not alien to physics. It is only alien to our daily experience. The challenge lies in scale. The Casimir effect produces negative energy densities, but only in tiny pockets and only under strict conditions. Holding a wormhole open would require negative energy on a scale far beyond anything we can generate or sustain. The throat of a traversable wormhole might be meters or kilometers wide, depending on its design. To stabilize it, you would need a vast, coherent source of exotic matter. No known mechanism can produce such a quantity. Even if the universe allows it in principle, the practical barriers are enormous. This is where the architecture of curved spacetime becomes fascinating. Exotic matter isn't merely a strange ingredient. It changes how spacetime moves around it. Positive energy curves spacetime in familiar ways, pulling objects inward, shaping the gravitational fields of stars and planets. Negative energy curves spacetime oppositely. It stretches, pushes, and maintains open structures that would otherwise collapse. In theoretical models, a thin layer of exotic matter lining a wormhole throat can keep it from pinching closed. The exotic matter serves as a kind of tension, resisting the geometry's natural inclination to seal off the shortcut. Quantum field theory offers additional frameworks in which negative energy appears. Some fluctuations in curved spacetime behave as though they borrow energy from the vacuum, creating temporary dips below the baseline. These dips are constrained by what physicists call quantum inequalities, which prevent negative energy from being too large or lasting too long. Nature permits the negative regions, but it tightly regulates them. That regulatory behavior may be one of the reasons wormholes remain theoretical. The universe may allow the geometry but refuse to support its long-term stability. When we imagine wormholes as engineering projects, we implicitly assume control over energy on a level we have never approached. Even a small wormhole would require mastering quantum fields with exquisite precision. We would need to create negative energy, concentrate it, and sustain it against competing quantum fluctuations. The process would demand new technologies, new materials, and new understandings of physics, likely ones that require insights into quantum gravity, the still elusive theory, unifying general relativity with quantum mechanics. In this way, wormholes sit at a crossroads. They reveal both the flexibility and the limits of space-time. General relativity allows the geometry, quantum theory allows the energy conditions, but neither framework gives us a clear path to scale the effects, control them, or prevent their decay. Wormholes become possible in the way a perfect crystal is possible, not forbidden, but exquisitely sensitive to environmental conditions. Any disturbance could cause collapse. Despite these obstacles, the mathematical consistency of exotic matter keeps the idea alive. It also pushes researchers to look at quantum vacuum structures more carefully. Some have explored the possibility that space-time contains natural pockets of negative energy at microscopic scales. Others investigate quantum fields near black holes where energy conditions are violated in ways that remain physically meaningful. These areas of study do not produce wormholes, but they deepen our sense that the vacuum is more dynamic than classical intuition would suggest. Whenever I think of exotic matter, I remind myself that the absence of evidence is not equivalent to impossibility. Before the discovery of gravitational waves, black holes were considered purely theoretical by many scientists. Before the detection of cosmic acceleration, dark energy was an idea without observational support. Physics progresses through a pattern: equations, predictions, skepticism, evidence. Exotic matter may remain forever in the first two stages. But the universe has surprised us before. Even if wormholes turn out to be unreachable, the attempt to understand them illuminates the architecture of space-time. It shows how energy shapes geometry, how quantum fluctuations influence large structures, and how the universe balances what is mathematically permitted against what is physically realized. Exotic matter occupies that narrow region between the conceivable and the unattainable. Thinking mathematically about wormholes inevitably leads to a broader question. If the geometry can be shaped, might there be other ways to exploit that flexibility without requiring impossible structures? It is tempting to imagine that a warp drive is simply a vehicle that moves faster than light. But relativity forbids that. Nothing with mass can outrun a light beam traveling through empty space. The limitation is not merely technological, it's woven into the structure of space-time itself. Yet general relativity allows something more subtle. You cannot move through space faster than light, but space-time itself can stretch or contract without violating any rule. A warp drive takes advantage of that distinction. The basic idea is elegant. Instead of accelerating the spacecraft, you contract the space in front of it and expand the space behind it. The ship rides inside a region of unchanging geometry, a bubble, while space-time around the bubble shifts. Inside the bubble, nothing breaks the speed limit. From the outside, the bubble appears to move rapidly across enormous distances. The mathematics resembles a controlled ripple moving through a pond, while the leaf floating at the center barely moves on its own. This concept emerges naturally from Einstein's equations. If you define the geometry you want, the equations tell you which energy distributions can produce it. The warp metric is one such geometry. It curves space-time in a particular way, compressed ahead, stretched behind, flat inside. Like wormholes, warp metrics are not forbidden. They are permitted solutions. They sit inside the space of mathematically valid possibilities alongside black holes, gravitational waves, and expanding universes. Yet permission from the equations is not the same as physical feasibility. The challenge appears immediately. The energy distribution needed to power a warp bubble includes negative energy. Not just a small amount, an enormous one. The curvature required to push space-time in such a directed way demands exotic matter, the same elusive ingredient that keeps wormholes open. Classical matter cannot produce the geometry. You need something that violates conventional energy conditions. This brings us back to the quantum vacuum. The vacuum can, in special circumstances, produce brief pockets of negative energy. The Casimir effect demonstrates this, but those pockets are tiny and unstable. The warp drive requires something sustained and large-scale. Even optimistic estimates suggest the energy needed would dwarf any resource humanity could access. Some early calculations even suggested more energy than the mass of the visible universe. Later refinements reduced the requirement dramatically, but it remains overwhelming. Warp drives also face a more subtle problem. They require careful control of curvature at the bubble's boundary. If the energy distribution fluctuates even slightly, the bubble becomes unstable. The front edge may collapse, or the rear edge may detach. In some formulations, information cannot escape the bubble once it is formed, meaning the spacecraft inside cannot steer or adjust the curvature from within. It becomes sealed off from the universe it is trying to travel through. The geometry protects the ship, but it also isolates it. Another complication arises from causality. When space-time warps dramatically, regions outside the bubble may become disconnected from regions inside it. Some versions of the warp metric risk creating horizons similar to those around black holes. Horizons are boundaries beyond which events cannot influence the observer. If a warp bubble creates such horizons, the pilot may have no way to access the controls that maintain the curvature. The ship becomes a passenger inside its own gravitational wave. Still, the idea persists for a reason. Relativity is generous with possibilities. The same equations that describe the slowing of time near a black hole also describe regions where space-time expands faster than light. Indeed, the universe itself has expanded faster than light in the past. During the brief epoch of cosmic inflation, space grew exponentially, carrying regions apart faster than photons could bridge them. Today, dark energy drives a gentler but still accelerating expansion. The cosmos is already stretching space-time faster than light in distant regions. This cosmic behavior suggests that propulsion through curvature is not an invention. It is a natural phenomenon scaled differently. The universe knows how to expand space. It has done so for billions of years. In principle, a warp drive is simply a localized, engineered version of expansion and contraction. The difference is control. The universe acts globally, following the large-scale behavior of its fields. A warp bubble would require local, deliberate manipulation of energy densities far beyond anything we can manage. Dark energy enters the conversation here. It has negative pressure, an unusual property that drives accelerated expansion. If we better understood the physics behind dark energy, we might someday learn whether its properties could be shaped or directed. At present, dark energy fills space uniformly. It does not clump or respond to forces the way matter does. But our understanding is incomplete. If dark energy is tied to vacuum energy or to geometry itself, then perhaps there exist configurations we have yet to discover. Even so, the gap between permitted and practical remains immense. No known form of matter can supply the necessary curvature. No experiment has created negative energy in quantities larger than the tiniest quantum fluctuations, and no theory unites quantum mechanics with general relativity in a way that reveals new pathways. Warp drives lie at the boundary of our imagination and our mathematics. They are not dismissed, but they are not imminent. When I teach advanced general relativity, I sometimes assign the warp metric as a thought exercise. Students attempt to calculate the required energy distribution and quickly discover the scale of the difficulty. The purpose is not to discourage them, but to cultivate a sense of humility. Physics invites speculation, but demands rigor. The warp drive belongs to this dual space, rigorous enough to be taken seriously, speculative enough to remind us that our scientific reach still has limits. Yet the thought remains powerful. Curvature, not velocity, determines the speed of cosmic expansion. If we ever learn to manipulate curvature, even in small ways, our concept of travel may change. Not faster ships, but different geometry. Not breaking the speed of light, but bending the stage on which motion occurs. When we speak about warp drives with caution and precision, we're not indulging fantasy. We're exploring the edges of known physics, testing how far general relativity can stretch before quantum mechanics reins it in. The boundary between the possible and the achievable is rarely sharp. And just beyond warp metrics lies an even deeper puzzle. The mysterious force already stretching the universe faster than any warp bubble could: dark energy. The phrase dark energy suggests mystery, but it also suggests darkness, and that part is misleading. Dark energy is not dark. It does not absorb light. It does not block starlight or cast shadows. It is transparent, quiet, and everywhere. If you held out your hand right now, dark energy would slip through your fingers as easily as empty space. Nothing in your body could detect it, and yet dark energy shapes the fate of the cosmos. The discovery came at the end of the 20th century, when two independent teams of astronomers were measuring the expansion of the universe using distant supernovae as markers. They expected to find that expansion was slowing down, pulled back by the gravitational attraction of matter. What they found instead was the opposite: the expansion was accelerating. Galaxies were not just moving apart, they were speeding away from one another faster over time. Something was pushing the universe outward. To explain this acceleration, physicists introduced the idea of dark energy, a term that functions more as a placeholder than as an explanation. It describes a phenomenon we can measure but do not understand. Roughly 70% of the total energy content of the universe appears to reside in this invisible component. All the stars, planets, gas, dust, and dark matter together form the remaining 30%. The thing we understand least dominates everything. The simplest interpretation is that dark energy is a property of the vacuum itself. Empty space, according to quantum mechanics, is never truly empty. It's seized with fluctuations, particles appearing and disappearing too quickly to observe directly. These fluctuations carry energy. If the vacuum has energy, it exerts pressure on space-time. A positive vacuum energy leads to negative pressure, a counterintuitive behavior in which space stretches faster as it expands. This vacuum energy interpretation aligns with Einstein's cosmological constant, a term he introduced in his equations to allow for a static universe. After discovering cosmic expansion, Einstein reportedly dismissed the constant as a mistake. Today, it returns with new relevance. A cosmological constant behaves exactly like dark energy, uniform, persistent, and woven into the fabric of space-time. The problem is not the idea, but the magnitude. When physicists calculate the vacuum energy using quantum field theory, the predicted value is staggering, over 100 orders of magnitude larger than what we observe. The universe should have torn itself apart instantly, yet the actual dark energy density is small, subtle, and strangely well-tuned. It appears just large enough to accelerate expansion today, but not so large as to dominate much earlier in cosmic history. We do not know why. Some researchers turn to extra dimensions for clues. In theories like string theory, space-time may have more than 4 dimensions, with the extras curled up at scales too small to see. The size and shape of these extra dimensions influence the vacuum energy. If their geometry changes over time, dark energy might reflect those changes. In this view, dark energy could be a geometric effect, rather than a substance, an emergent property of how higher dimensional space folds into our observable universe. Others explore dynamic models in which dark energy evolves. Instead of being constant, the energy density could shift, slowly governed by a field that permeates space. This field would be nearly uniform but capable of subtle variations. If dark energy evolves, the cosmic acceleration might change over billions of years. We may live in a transitional era, not a permanent state. Despite these possibilities, no model has gained universal acceptance. Observations continue to refine our understanding, but they have not pointed to a definitive explanation. The cosmic microwave background, the distribution of galaxies, and measurements of supernovae all favor a simple cosmological constant. Yet simplicity does not guarantee understanding. We know dark energy behaves like a constant, but we do not know why. Dark energy also challenges our intuition about gravity. Gravity should pull things together. Yet in the presence of dark energy, the universe expands faster. This suggests that gravity is not weakened. Rather, the geometry of space-time itself is being pushed outward. Gravity responds to energy, not just mass. If the vacuum contains energy, then space-time curves accordingly. What surprises us is the direction of that curvature. Whenever I think about dark energy, I'm struck by its silence. It does not clump. It does not form structures. It does not interact with matter in ways we can detect. Yet its influence reaches across billions of light years, shaping the acceleration of cosmic expansion. In the far future, galaxies will drift so far apart that their light can no longer reach one another. The universe will fragment into isolated islands of matter, each surrounded by an ocean of unobservable space. Dark energy drives that fate. Understanding dark energy may require a breakthrough in quantum gravity, or an insight into the topology of space-time, or perhaps a new perspective entirely. It may turn out to be simpler than we think, or more complex than any current model allows. For now, we sit with a paradox. The most dominant component of the universe is the one we grasp the least. The enigma of dark energy naturally leads to the companion puzzle of dark matter. One shapes the universe's expansion, the other shapes its structure. If dark energy pushes, dark matter pulls, and unlike dark energy, we can track its gravitational influence in exquisite detail. It leaves fingerprints in the way galaxies cluster, in the way light bends, and in the way cosmic structures form. When I talk about dark matter, I often begin with a simple statement: we do not see it yet. We see exactly what it does. The evidence is not a whisper or a hint. It is overwhelming, layered, and consistent. Dark matter shapes galaxies, bends light, steers cosmic evolution, and composes far more of the universe than the atoms we are made of. If dark energy defines the universe's expansion, dark matter defines its structure. The earliest clues came from the rotation of galaxies. When astronomers measured how fast stars orbit around their galactic centers, they expected the outer stars to move more slowly than the inner ones, the way distant planets orbit the sun more gently than those closer in. But galaxies refused to follow this rule. Stars far from the center were moving too quickly, as though held by an unseen gravitational tether. The visible matter-gas dust stars was insufficient. Something else had to be providing the missing gravitational pull. Gravitational lensing offered a second line of evidence. According to general relativity, mass bends space-time, and light follows those curves. When astronomers observed the distorted arcs of distant galaxies behind massive clusters, they could calculate the mass responsible for the bending. The result was always the same: far more mass existed than what could be seen. Light revealed structures that matter refused to show. It became clear that the majority of mass in galaxy clusters was invisible, dark, not in color, but in interaction. One of the most compelling observations came from a system known as the bullet cluster. Two galaxy clusters collided in a violent encounter, sending gas clouds crashing into one another and slowing down as they interacted. But the gravitational lensing maps told a different story. Most of the mass passed straight through the collision, without slowing at all. The luminous matter stars and gas became separated from the bulk of the gravitational mass. The visible material lagged behind, the unseen mass drifted ahead. It was a clean, indisputable demonstration that something non-luminous, non-interacting, and massive permeates these systems. If dark matter interacted strongly with ordinary matter, it would have collided like the gas clouds. Instead, it slipped through as though it were nearly transparent. This behavior is one of the reasons scientists describe dark matter as collisionless. It interacts gravitationally but not electromagnetically. It does not shine, absorb, scatter, or reflect light. It does not produce chemical bonds or form atoms. It reveals itself only through gravity, the most patient, least intrusive force in nature. Yet the term dark matter does not point to a single substance. It is a category defined by what we observe gravitationally. Within that category, several candidates exist. Neutrinos are one example. Trillions pass through your body every second, emitted by the sun and by cosmic phenomena beyond our galaxy. They are technically a form of dark matter because they do not interact with light. But they are too light and too fast to account for the missing mass. They slip through galaxies without contributing enough gravitational pull. They cannot be the primary dark matter component. Another possibility is that dark matter consists of particles we have not yet detected, weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass and would interact through a weak nuclear force, but so faintly that they pass through matter almost entirely unnoticed. For decades, experiments have searched for rare collisions between WIMPs and atomic nuclei. So far, no definitive detection has emerged. Still, the absence of evidence does not weaken the case for dark matter itself. The gravitational evidence is overwhelming. Galaxies form, rotate, and cluster in patterns that cannot be explained without large halos of invisible mass surrounding them. Computer simulations of cosmic evolution fail entirely unless dark matter is included. The cosmic web, the vast network of filaments that connects galaxies across billions of light years, forms correctly only when dark matter acts as scaffolding, guiding the flow of ordinary matter. Some have proposed modifications to gravity rather than new matter. These ideas attempt to tweak Einstein's equations or introduce new gravitational behaviors at large scales. But these models have struggled to reproduce the full suite of observations. Gravitational lensing in particular remains difficult to explain without actual mass. The bullet cluster stands as a challenge to modified gravity theories. The separation of mass and light demands an invisible mass component. Dark matter does not need to be exotic in the sense of violating known physics. It simply needs to be non-luminous and weakly interacting. In principle, it could be a particle that fits naturally into extensions of the standard model of particle physics. Or it could belong to a deeper symmetry of nature that we have yet to discover. Dark matter might even be a collection of different particles, not a single species. The quietness of dark matter is part of what makes it captivating. Its presence is unmistakable, yet it rarely announces itself. It does not collide, burn, freeze, or decay in ordinary ways. It forms vast halos around galaxies and drifts through the universe like a ghostly scaffold. The Milky Way moves through a sea of dark matter right now, and you move with it unaware. Whenever I talk about dark matter, I'm struck by how confident the scientific community has become about its existence. In the early decades, skepticism was common. Perhaps the measurements were wrong. Perhaps our understanding of gravity was incomplete. But over time, the evidence accumulated across independent methods, across wavelengths, across cosmic epochs. The consensus grew not through belief, but through constraint. Every alternative that excluded dark matter failed to account for something critical. The invisible became the inevitable. There is something humbling in the realization that most of the matter in the universe escapes our senses entirely. Our bodies, our planets, our stars, all made of baryonic matter, constitute a minority. The dominant form of matter is quiet, cold, and hidden, and yet without dark matter, galaxies would not hold together, cosmic structure would unravel, and the universe would look nothing like the one we inhabit. The existence of dark matter leads naturally to a broader question. If most matter is invisible, what else might be hidden in the universe? The answer begins with a different kind of signal, not mass, but motion. Not light, but ripples in space-time itself. Those ripples carry the signature of some of the most violent events in the cosmos. There are moments in science when an idea moves from speculation to certainty, not because we change our minds, but because the universe finally speaks in a voice we can hear. Gravitational waves are one of those voices. For a century, they lived only in Einstein's equations, ripples in space-time predicted but never detected. The mathematics said they should exist. The universe remained silent, and then, after decades of effort, the silence broke. To understand gravitational waves, it helps to step away from the usual metaphors of gravity as a force, and instead think of space-time as a kind of medium. Not a fabric in the literal sense, but a structure that can curve, stretch, and vibrate. When two massive objects orbit each other, especially black holes or neutron stars, their motion stirs space-time. If the motion is violent enough, the curvature sends out ripples. Those ripples travel at the speed of light, carrying information about the event that created them. The closest analogy is sound. Not because gravitational waves travel through air, they don't, but because they behave like pressure waves in a medium. They expand and compress distances, stretching and squeezing space itself. If space-time were a drumhead, black holes would be the mallets. A binary system spiraling inward taps out a rhythm, each orbit tightening until the final collision produces a sharp, ringing crescendo. That oscillation, subtle, faint, but real, travels for billions of years before reaching Earth. When gravitational waves pass through your body, they alter the distances between atoms by an amount far smaller than a proton's diameter. You can't feel it. No instrument in daily life can detect it. Even the Earth does not notice. To hear such a signal, you need a detector that measures changes in length far smaller than the wavelength of light itself. That need led to one of the most ambitious physics projects ever undertaken, the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two facilities separated by thousands of kilometers, each shaped like a giant L. Each arm of the L stretches 4 kilometers across. A laser is split into two beams that travel down the arms, bounce off mirrors, and return to the point of origin. If space-time stretches or compresses along one arm, the returning light takes a slightly different amount of time to complete the trip. Even a difference of 1/10,000th the diameter of a proton leaves a measurable fingerprint in the interference pattern of the light. Building a machine capable of detecting such a delicate signal required decades of commitment. The idea was first conceived in the 1970s, led by Ray Weiss at MIT. His early calculations revealed not only that the measurement was possible, but that nothing about it would be easy. Seismic noise, passing trucks, temperature fluctuations, quantum fluctuations of the laser itself, each posed a threat to the signal. The list of obstacles was nearly endless. Weiss persisted anyway. Later, Kip Thorne at Caltech became a champion of the idea, pushing the theory forward and building a community around it. Barry Barish provided the large-scale leadership that transformed LIGO from a vision into a functioning observatory. Together with hundreds of researchers, engineers, and technicians, they constructed a machine so sensitive that it borders on the surreal. LIGO can detect a change in distance smaller than 1 part in 10 to the 21st. It can hear space-time tremble. Despite the ambition, early runs produced no detections. The detectors needed improvement. The instrument was redesigned, upgraded, and rebuilt. Entire careers passed without a confirmed signal. Some scientists wondered whether gravitational waves would always remain just beyond reach, as elusive as they were promised to be. The project continued anyway, driven by the belief that the universe was speaking. We simply needed to learn how to listen. Then, in September 2015, the detectors recorded a signal so clear it was unmistakable. 2 black holes, each several tens of times the mass of the sun, spiraled into one another more than 1 billion light-years away. The waveform showed the frequency rising as the black holes approached, then peaking at the moment of merger, followed by a ring down as the newly formed black holes settled into shape. It was the exact signature predicted by relativity. The signal was faint, brief, and perfect. The detection changed gravitational physics overnight. Black holes were no longer abstractions. They were objects we could listen to. The merger released a burst of energy so immense that for a fraction of a second, the power radiated as gravitational waves exceeded the light output of every star in the universe combined. Yet by the time the waves reached Earth, they stretched space-time by a fraction so tiny that only LIGO could detect it. What struck many of us was not only the achievement, but the human story behind it. Decades of uncertainty, years of doubt, experimental setbacks, the sense of standing at the edge of the impossible, and then finally the universe answered a question first asked a century earlier. The signal arrived almost immediately after the upgraded detectors began collecting data, as though the cosmos had been waiting patiently for us to build the right instrument. Since that first detection, LIGO and its partner observatories have recorded dozens of gravitational wave events, black hole mergers, neutron-star collisions, and perhaps signals yet to be fully classified. Each detection enriches our understanding of extreme physics regions where gravity becomes so intense that space-time bends violently. These events cannot be seen directly. They are hidden by darkness, distance, or both. Gravitational waves offer a new sense, a new way of observing the cosmos. Listening to these waves reshapes our concept of the universe. Instead of viewing the cosmos as a silent expanse, we begin to hear it, not metaphorically but mathematically. The oscillations reveal mass, spin, distance, and energy. They carry the memory of catastrophic events that unfolded long before humans existed. They remind us that space-time is not static, but dynamic and alive with motion. Every new detection also deepens an old idea: the universe may be filled with signals we have not yet learned to perceive. Gravitational waves were invisible until we built machines that could hear them. Dark matter was invisible until we tracked its gravitational lensing. Dark energy was invisible until we measured the expansion of distant galaxies. Each discovery teaches us to refine our senses, literal and conceptual. There are regions of the universe we cannot reach, and there are regions of thought we cannot cross. The first is a matter of physics, the second is a matter of logic. Both boundaries reveal themselves through limits not of imagination, but of what the laws of nature and the structure of reasoning allow. When I think about these intellectual boundaries, I inevitably think of 2 figures whose work reshaped the foundations of mathematics and computation: Kurt Gödel and Alan Turing. Gödel arrived at a moment when mathematics seemed poised for completion. Many believed that all truths could be derived from a consistent set of axioms. Logic would provide certainty. Formal systems would serve as a foundation beneath all of mathematics. But Gödel saw something different. His insight was that any sufficiently powerful logical system contains statements that are true, but cannot be proven within the system itself. His incompleteness theorems were not a setback. They were a revelation. They showed that truth exceeds proof, that the landscape of mathematics is larger than any map we can draw of it. The precision of Gödel's reasoning contrasts sharply with the fragility of his life. He was brilliant, meticulous, and deeply introspective, but his mind carried the same intensity that made his logic so powerful. Over time, his anxiety deepened into paranoia. He trusted only a small number of people, one of them, Albert Einstein, with whom he walked to Princeton's Institute for Advanced Study nearly every day. Einstein once said that these walks were what made going to the office worthwhile. Gödel's genius was not separate from his fragility. It lived alongside it. His work proved that limits exist not because we lack skill, but because the universe imposes them. Knowledge has boundaries. Certainty has cracks. While Gödel exposed the limits of proof, Alan Turing illuminated the limits of computation. Turing showed that even with a perfectly logical machine, his idealized universal machine, there are problems that cannot be solved. Some questions have no algorithmic answer. No amount of computation, no matter how fast or sophisticated, will ever produce a solution. The boundary is absolute. Turing's work is often remembered for its role in creating the field of computer science, but the deeper insight is conceptual reasoning itself is bounded. There are truths we cannot compute and patterns we cannot predict. The human desire for completeness meets the universe's refusal to provide it. Outside mathematics, Turing's brilliance turned toward cryptography during the Second World War. At Bletchley Park, he played a central role in breaking the German Enigma code, shortening the war and saving countless lives. This achievement required an unusual blend of logic, intuition, and engineering. Turing built machines to break machines using the structure of the code against itself. His success reshaped intelligence work and gave birth to computing as we know it. Yet Turing, like Gödel, lived a life marked by vulnerability. He faced persecution, suffered isolation, and ultimately met a tragic end. His contributions were classified for decades, known only to a small circle. By the time the world recognized his genius, he was gone. His story reminds us that ideas can endure even when the people who discover them cannot. Both Gödel and Turing worked at the edge of what is knowable. Their theorems are not just mathematical, they are philosophical. They reveal that the universe has boundaries not only in space and time, but also in logic. We cannot prove every truth. We cannot compute every outcome. We cannot design a perfect system that explains everything without contradiction. These limitations are not failings of intellect. They are structures built into reality. Whenever I reflect on their work, I'm reminded of how science often advances not by expanding certainty, but by clarifying where certainty stops. Gödel showed that truth is larger than proof. Turing showed that problems exist beyond computation. Their discoveries place constraints on human understanding, but they also expand it by mapping the edges. There is also a human dimension that lingers behind their work. Genius is not a guarantee of peace. The same mind that grasps profound truths can also struggle with its own shadows. Both Gödel and Turing paid a price for their brilliance, though the nature of that price differed. Their lives remind us that the pursuit of knowledge is not separate from the people who pursue it. Insight and vulnerability often coexist. The limits they uncovered echo across physics as well. Just as there are unprovable truths and uncomputable problems, there are cosmic boundaries we cannot cross. Light speed barriers, horizons around black holes, distances that expand faster than we can traverse. The universe has its own incompletenesses, regions, forever hidden phenomena that remain beyond observation. Gödel himself once proposed a rotating universe solution to Einstein's equations, a cosmology in which time loops on itself. In such a universe, the distinction between past and future dissolves. Causality becomes tangled. Though the solution is mathematically valid, it does not appear to describe our universe. Still, it illustrates an extraordinary idea. Relativity, too, contains logical boundaries and strange possibilities. Gödel's universe isn't our universe, but it shows that the laws of physics allow geometries far stranger than our experience suggests. Turing's legacy also intersects with modern physics. Quantum computing, still in its early stages, pushes against the limits of what machines can calculate. While quantum computers may solve certain problems more efficiently than classical machines, they do not break the boundaries Turing established. The uncomputable remains uncomputable. These insights mirror our journey through earlier chapters. Wormholes are allowed mathematically, but perhaps not physically. Warp drives are permitted by equations, but forbidden by practicality. Dark matter is detectable only through gravity, and dark energy is measurable but still mysterious. The universe seems composed of accessible knowledge stitched together with impenetrable regions, not unlike the structure of logic itself. As we move through these ideas, another question begins to emerge. If understanding is bounded, what remains? What does it mean to explore a universe that may always exceed our comprehension? And how do we find meaning in a cosmos destined to forget everything from its galaxies to its observers? When I think about the universe far into the future, I picture not a dramatic ending, but a quiet one. No explosions, no sudden collapse, just a gradual dimming. A long exhale across unimaginable time. The cosmos appears vibrant to us now, galaxies, shining stars, forming matter interacting. But the physics we know points toward an era when even the brightest structures fade beyond reach, carried away by the accelerating expansion driven by dark energy. Imagine galaxies as lanterns scattered across a dark plane. As the space between them stretches faster and faster, each lantern drifts until its light can no longer reach the others. The night becomes emptier not because the lanterns go out, but because the distance between them grows too quickly. One day, distant galaxies will slip beyond our cosmic horizon, receding faster than light can travel. They will not vanish, they will simply become unreachable. Astronomers of that distant era, if any remain, will see only the remnants of their own small island of stars. The wider universe will be lost to memory. This erasure is not violent. It is simply the natural consequence of the laws that govern expansion. Just as gravitational waves travel through a changing cosmic landscape, so too do galaxies drift through expanding space. Gradually, the universe forgets its own history. Evidence of the Big Bang fades. Background radiation cools. Structures disperse. Black holes evaporate. Even the information encoded in particles drifts into thermal equilibrium until distinctions blur. When I teach cosmology, students sometimes find this trajectory unsettling. It feels counter to our desire for permanence. We build tools to understand the universe. We write equations to describe it. We leave traces in the form of ideas, machines, observations. Yet physics suggests that in the far future, all traces will dissolve. Not because they were weak, but because the universe is unyielding. Entropy increases. Energy thins. Everything spreads out. This future is not a failure of meaning. Meaning belongs to the beings who look at the universe now, not to the universe millions of trillions of years from now. The fact that our work, our stories, and our discoveries are temporary does not diminish their value any more than the setting of the sun diminishes the beauty of daylight. If anything, impermanence sharpens attention. Knowing that nothing lasts forever invites us to experience what exists while it exists. The physicist Freeman Dyson once imagined that intelligence might find ingenious ways to persist even as energy becomes scarce. Others speculate about civilizations migrating between stars, storing information in black holes, or manipulating space-time to survive. These ideas are fascinating and speculative, but even the most optimistic scenarios eventually collide with the constraints of thermodynamics. The universe trends toward uniformity, structure dissipates, and yet there is something comforting in acknowledging limits. The universe does not promise eternal memory. It offers moments where matter is arranged, just so allowing planets to form complex chemistry, to flourish, and observers to wonder. We are one such moment. Temporary, yes, but extraordinary. When I think about Gödel and Turing, about black holes ringing space like a drum, about the wormholes that may exist only in the equations we manipulate, I'm reminded that curiosity is itself a form of resilience. We explore not because the universe guarantees answers, but because the act of looking brings clarity to our own brief existence. The discoveries we make today may fade billions of years from now, but they matter to us here in this era where the night sky is still full of galaxies. If there's a unifying thread through everything we've explored, from the gray transition between non-living and living matter, to the strange geometries of wormholes, to the shadowy components of dark matter and dark energy, to the limits of logic revealed by Gödel and Turing, it is this: the universe is richer, stranger, and more intricate than any final theory could capture. Some truths remain beyond reach. Some boundaries cannot be crossed. But within those boundaries, we trace patterns, solve puzzles, and build meaning. In a universe destined to forget, it becomes even more important that we remember, that we chart the sky, that we listen for gravitational waves from black holes that merged long before life existed on Earth, that we decode mathematical limits, that we contemplate the edges of knowledge. The universe may erase the record, but while the record exists, it transforms us. I sometimes imagine drawing a pattern in the sand, something delicate, intricate, maybe beautiful. The tide will eventually wash it away, but the act of drawing matters while it unfolds. The motion of the hand, the pattern appearing, the moment of understanding. The universe, too, is a tide, one that will eventually smooth every contour. But right now, in this brief cosmic window, we can shape ideas, share insights, and contribute to the fragile chain of discovery. So what remains in a universe that forgets? As you rest now, you carry with you the same raw material that composes stars, planets, and the earliest structures of the universe. The atoms in your body were forged in environments more extreme than anything we can recreate on Earth. And yet here they are, arranged in a way that allows you to think, to feel, to wonder. Thank you for spending this time with me, letting the questions stretch out softly in your mind. Wherever your thoughts drift as you fall asleep, I hope they move with a sense of ease, a reminder that even in a vast and fading universe, moments like this can be quietly luminous.